Okay, thank you. Hello, everyone. Okay, so I will speak about the quotients of Cremona groups. And so since I am the first speaker this week, okay, let me give the definition of a Cremona group just so that everyone actually knows. So, the Cremona group of rank n over a field K is the group of birational transformations so birational maps defined over K. Of rank n over a field K. Okay, good. I guess this shouldn't be something new, since you have been here one of the weeks before. Okay, so the main question that I want to address today and tomorrow is the following, namely, which quotients, or maybe what kind, of quotients does the Cremona group Rn of K admit? So this is a bit of a vague question, but it will become, well, you will see what I will say, so it will become more clear. And so, in other words, so what I ask about is about the group homomorphisms from the Cremona group surjective onto a group G. Okay, so this is what quotients mean. And so some related questions are, so first about the normal subgroups. Okay, because if you have a group homomorphism, you take the kernel, that's a normal subgroup, and all normal subgroups you can take the quotient. So it's the same, it's kind of the same question, but it's like from a different point of view. And about the abelianization of the Cremona group. So abelianization, this means basically we want to know which abelian quotients exist. And then the abelianization is kind of the largest abelian group that is a quotient. Okay. So there are several constructions of quotients or several results to these questions. And they use different techniques. And I think this is one of the nice features of Cremona groups, that a lot of different techniques are being used to study the same object. So there are several constructions using different techniques. By the way, am I writing large enough? Yes? Okay, good. Okay, so the first technique I want to mention is a geometric group theory. And so let me give a name. So Conta, Lamy, and Lonjou have used geometric group theory to construct normal subgroups. So in the case for n is 2. Okay, and so I will be just very vague. So they show that there exists H in CR2 of K, such that when you take the normal subgroup generated by this element H to some power, maybe R. So this gives a proper subgroup of the Cremona group. Okay. So they use a geometric group theory, a small cancellation, small cancellation property. They find such a H, and then, well, using techniques, they can show that this is in fact a normal, proper subgroup. Okay? So in this way, so here they really take the point of view of the normal subgroups, and so with this technique, it is so we can take the quotient, but it is unclear, like how to describe the quotient. Okay, so they really take the point of view of the normal subgroup and not of the quotient. Okay. Then the second technique that is the one that I will focus on. So the second technique is using generators and relations. And so this will mostly be with using the Sarkisov program. So here the idea is that we know some generators and relations, and we somehow can control them well enough to obtain quotients of the group. So, so there are several constructions using this technique. So I will just now give an overview of them, and then later I will focus on some specific ones. So for n is 2, we have several constructions where the quotient G can be written in the following form. Free product, direct sum, set modulo 2, with some indexing sets where I don't want to be precise. Okay, and so here I want to say that, so let me say one thing. So if K is not algebraically closed, then there exists a quotient. There exists such a quotient such that, so first of all, that J is not empty, and so the cardinality of the indexing set I here is at least the cardinality of n. It's at least countable. Okay, so just to say, so we have different we have different constructions, but like several ones, like highlighting different, using different maps, and okay. But what we can say is that if K is not algebraically closed, then we have an uncountable direct sum of set mod 2s. I want to give some names here. So constructions are, so first I want to mention Zimmermann. So in fact, she described the abelianization. So she was working over the real numbers, and she can describe the abelianization of the Cremona group. So let's maybe say CR2R abelianization is equal to a direct sum over indexing set of the cardinality of R. Let's maybe write it in this way, of set modulo 2. Then, together with Stéphane Lamy, they made another construction that works for many fields. Yeah, so let me stop here. Okay. And so let me mention maybe also, so here we always have this set modulo 2 for in all the constructions that we have for surfaces. And in fact, so maybe a remark, or yeah. I guess the theorem is by Lamy and myself. And we showed that CR2K is generated by involutions. So for any perfect field. Now I want to mention this because this is an obstruction to having other abelian quotients than set mod 2. Because it's generated by involutions, we need to have this set mod 2 if it's abelian. Okay, but now let's go to higher dimensions. So if n is at least 3, then there are construction of quotients of, and let's maybe say, so in higher dimensions I will usually think of the complex numbers. So dimension 2 over, let's say, perfect fields or maybe any field, but in higher dimensions I want to work over C. And then again we have like constructions. Now again we have different constructions, but let me mention one construction. So and there we have cardinality of C. So this is due to Blanc, Lamy, Zimmermann. But so I mentioned there are also other constructions, and then we get other indexing sets. I don't want to specify much more, but I just want to give the names. So we have Blanc-Jasinski, and we have a construction by Tsikas, and these are for dimension 3. Okay. Then there is, okay, so this was now all. So all these constructions are using generators and relations, and more specifically the Sarkisov program. But there is a third technique, and this is using a motivic invariance. So if you have been here for the first week, I guess you will have seen this. But so just very quickly. So here done by Lin and Schindler. And so what they do is they take a birational map. And then they send it onto, so they take the exceptional locus of F and do it minus the exceptional locus of the inverse. And they study this, so the ones of the subvarieties of dimension n minus 1. Let me write it in this way. What did I? Yes, absolutely. Thank you. Yes. Yes. And they look at this object in. So let me write it in this way. So they look at it in the free abelian group of beer n minus 1 over, okay. Okay, so this is the free abelian group on the set of the, okay, let me write it out. Free abelian group on the set of birational equivalence classes. Of n minus 1 dimensional subvarieties. So here they take a birational map and they, so looking at the map, you can define this group homomorphism. So like you can define the image of this group homomorphism. And there is a variant of this construction done by Genevois, Lonchou, Urech, where they look at the same thing, but not inside the birational equivalence classes, but of Cremona equivalence classes. So they look the same thing, but inside set of the divisors of Pn modulo Cremona equivalence. Okay. And I should mention, so what they find, so what they find is they find a quotient G, which is a direct sum of Z. So I should say this is for n at least 4. Okay. Okay, so we see that for dimension at least 4, all of a sudden we get this quotient of Z. Okay. And in fact, there is also a stronger result using the Sarkisov program. So I will write this down here. So if n is at least 4, we find so complex numbers. There is also a quotient which has the shape Are there questions? No, please. Okay, so for dimension at least 4, so I should mention, so this is a Blanc together with Jasinski. And now this, since we have such a quotient, in fact, there are many more quotients. So in fact, this means that every group is a quotient of the Cremona group. Like, G with cardinality, at most the cardinality of the Cremona group, which is the cardinality of C, is a quotient. This is just a group theoretic consequence. Yes, thank you. Okay, so just because this here is here, this is the free group on the set of cardinality C. But then, yeah, there is not so much information about like when it's just a group theoretic quotient that you take then. So okay. So also with these constructions, they also have some corollaries, or maybe corollary is not the correct word, because it's like the construction of the quotient together with some additional work. And these consequences, they are kind of negative results. Because in the sense that, like for example, if we take this quotient here, this means that the Cremona group is not generated by elements of finite order. Because, sorry, here when we have so this is for n at least 4, and so I should say K is C. Because then we have this theorem, so now if the Cremona group were generated by elements of finite order, you need to send the generator somewhere and then to an element of finite order. But here in the quotient we have elements of infinite order. So in this sense, this is like a negative result for the generating set of the Cremona group. And also with, so maybe I can say this orally. So just like to give you an idea of, what this leads to. So for n at least 3 and k equals C, for example, the construction by Blanc and Jasinski, as a consequence, they have that, so n equals 3, that the Cremona group is not generated by any connected algebraic subgroups. So you take all connected algebraic subgroups, you take the group that they generate, and you still don't get everything. So this is not an immediate consequence of the quotient, but like they analyze what is in the kernel, and they find that all these groups are in the kernel. So they can't generate the whole group. Can you repeat, please? Is it the one with like the toric map? No. Yes, this one. So toric maps are always in the kernel. This is the result. Okay. So also, if you take the automorphisms and the Jonquière elements and any fixed set, which has the cardinality smaller than your field, this is also not enough to generate the Cremona group. And also, so here, with the construction by Lin and Schindler, as a consequence, I get that the Cremona group in these cases is not generated by pseudo-regularizable elements. Because again, all pseudo-regularizable elements end up in the kernel of this map. Okay. So, okay, so this was a bit of an overview of several results that we have. Are there questions? So now what I want to do is I want to focus on these techniques of generators and relations of the Sarkisov program. And so today I want to speak about the constructions in dimension 2 and tomorrow constructions in higher dimensions. Okay. So I know now it was just a bit of a mix of stuff, but okay. I guess I should keep this. Okay. Okay, so I want to start with a small remark, or maybe small lemma or something, but small. So let phi from a Cremona group CRNK to G be a group homomorphism. Then we are in one of the following two cases. So either G contains PGLN plus 1. So I will do over the complex numbers. Or we have that the group generated by PGLN plus 1 of C and the standard involution of degree n. So let me write it, let's call it sigma n, that maps in a fine, so I use affine coordinates, x1 up to xn onto 1 over x1, 1 over xn. So I take the group generated by this, and then this lies inside the kernel of phi. So we're one of these two cases. So why is this the case? So indeed. So we have that PGL n plus 1 of C. This is PSL n plus 1. And this is a simple group. So if we take the restriction of our phi onto PGLN plus 1, the kernel is a normal subgroup. But every normal subgroup is either, well, it's trivial, so it's either just the identity or it's everything. So this means that either we are in case 1. So this is in the case that the restriction, well, is everything, like is. So either we're in case 1, or we have that phi restricted to PGLN plus 1 of C is just the neutral element of the group. And okay, so now we have to look at the involution. And so I wrote this down somewhere. So now we can write this as a composition of phi alpha phi inverse, where we have the following. So phi, so where phi sends, in affine coordinates, it sends xi onto xi minus 1 divided by minus xi plus 1 for all I. And alpha sends xi onto minus xi. So you can check that indeed when you do this, you get the involution. If I didn't make a mistake, but I think it should be okay. Okay, so now this means that, so if we are in the case where the group homomorphism is trivial on PGLN plus 1, so this means that alpha is sent onto the trivial element, but then we have here phi inverse. So this is also mapped onto the trivial element, so we get the second case. So we are in case 2. And so just to say, so this involution, it is conjugate to a linear map, but with birational maps, so that the phi is birational. Okay. So, and I also want to take this remark here as a motivation that we will, later on, the constructions that we will see, that we will look at, we will always send the automorphisms onto 0. So in our constructions, automorphisms will not survive. Okay, so now I will start with the Sarkisov program. So I know that you have already seen this last week. So actually, could you please maybe raise your hands if you have been here last week, just like to see whether everyone has been here? Okay, not everyone, but a considerable amount. Good. Okay. Yes. Yes. So today I will speak about surfaces, so you have seen it. And have you also seen rank R fibrations? For surfaces, yes? Okay, good. So I will just quickly say, I will quickly say it. Okay, so now we go to the Sarkisov program. So today for surfaces. Yeah, I will still give the definition, otherwise it's a bit weird. So vibration pi from a surface X to B is a rank R vibration if the following holds. So we want X be smooth, X be smooth, dimension of B strictly smaller than the dimension of X, so smaller than 2. We want that to end relative pica rank of X over B is equal to R, and the anti-canonical divisor is pi ample, so relatively ample over the base. So this is the definition of a rank R vibration. Now I assume that you have seen this. But if there are questions, please. And then yes, so surjective morphism, so characteristic 0, it's connected fibers, yes, and otherwise a push forward of structures. This structure. And so now if we have a rank 1 vibration, so if X over B is a rank 1 vibration, then this is exactly the same as to say that X over B is a Mori fiber space, denoted by MFS. Okay. And if we have a rank 2 vibration, Y over B, then we obtain a diagram as follows. So we have Y over B, and we can decompose this map into this diagram, X1 over B1, X2 over B2 over B. And then now a Sarkisov link is now any birational map between two Mori fiber spaces that satisfy such a diagram. So let me write it down. So a birational map from X1 over B1 to X2 over B2, so between Mori fiber spaces. To Mori fiber spaces. Is a Sarkisov link. If it satisfies such a diagram. So let me call this diagram star. So if it satisfies a diagram as in star, where Y over B is a rank 2 vibration. Okay, and example. Maybe you have seen this example already last week. So let's start with P2. Let's blow up a point of degree 3, which is in general position. We obtain a Del Pezzo surface of degree 6. And so let me just. So geometrically, we have 3 points in general position. We blow it up, and then we can contract the orbit of lines going through the 3 points. So we have a contraction here onto a point of degree 3, and we go back to P2. And so now here we have a birational map from P2 to P2. Now this is all, we can look at this over spec K. And so Y6 has pica rank 2. So Y6 over spec K. Well, okay, so what do you want to say? So rho of this is just rho of Y6, and this is equal to 2. Because I blow up, so here we have pica rank 1, I blow up one closed point. So this has rank 2. Okay, and it is del pezzo, so Y6 is del pezzo. So del pezzo means that minus kx is ample, and so it's relatively ample. So in this sense, sorry, I think my Blackboard skills today are really not good, but okay, this is the example. Okay, and so now Y6 over spec K is a rank 2 vibration. So okay. Okay, and now the Sarkisov program tells us that these Sarkisov links generate birational maps. So I will be more precise. Okay, so we have the groupoid Mori of X, and let's say that X admits, assume that X admits a Mori fiber space structure. So for example, P2. So this is a groupoid, and it is defined with objects. Objects are Mori fiber spaces, so X over B Mori fiber space, such that X is birational to, so now X is not a good word. Yeah, I don't know, like X tilde, such that X tilde is birational, X tilde birational to X. And the morphisms are not just birational maps between, so if we have a Mori fiber space X1 over B1 and X2 over B2, then we take the birational maps between X1 and X2. So these are the morphisms in this groupoid. And now the theorem of the Sarkisov program is that this groupoid is generated by Sarkisov links and isomorphisms of Mori fiber spaces. And we also have generating relations, which thing which we call elementary relations. And trivial relations. Does this look familiar? trivial relations. I will explain in a second. So first I want to, so now we have a groupoid and we say, okay, it's generated by some elements and it has some relations. So I want to give an example of a groupoid in terms of generators and relations. So example of a groupoid in terms of generators and relations. So I want to do this so that, because I think it will help to fix some ideas. So let's take, so this is an example, okay? A priori, it has nothing to do with Sarkisov links, okay? Just an example. So I take the groupoid with two objects. So let's say S and S prime are two objects. And the morphisms, so I don't want to write down all the morphisms, but so I will just give you generators. So generators, I give you two morphisms. So one is a morphism that goes from S. So both of them, okay, yeah. So we have, I take two morphisms from S to S prime, A and B. Okay, so I have two objects and two morphisms, both of them go from S to S prime. So now because I take the groupoid generated by these morphisms, of course this also means that we have an identity, that we have a one morphism on S and on S prime. And of course we also have the inverses. So we have also A inverse going from S prime to S and B inverse. And of course we can also compose. So if I do A, then I can do B inverse. So I have A, B inverse, and so let me draw a picture. So, okay, now I want a lot of space. So let's say I start like at S. I can do A. I go to S prime. If I do A, so I am in S prime. So on S prime, I can do A inverse, or I can do B inverse. So let's say, okay, let's say in S, I can do either A or I can do B. Or I can do the identity on S, but okay, let's not draw it. Okay, and so here I am also in S prime. So after I do A, I can do B inverse, and I am at S again. So now I'm in S. I can either do B inverse, or I can do A. And I go to S prime. Okay, and so we can continue in such a way. So now I am in S prime, so I can do B inverse. I'm in S. Now from S, I can do A again. And now I want to do it one more time, I think. I will do B inverse. And I am back in S. Okay. There is identity. Yes. So I mean there is identity on S and there is identity on S prime. Yes. Okay, so now this groupoid, this is like the free groupoid on two objects and two morphisms. So I want to think of this as like maybe the free group on the set of morphisms A, B, where A and B go from S to S prime. Okay. Or maybe I also want to write this as like A, B, so generated by A and B. Okay. So now, so far I have no relations. So now I want to add some relations. So now an example with relations. So for example, I can now say, I want to say that, so if I do all of this, then this is the identity. Okay? So for example, this, I would write this as AB, such that a B inverse power 3 is the identity on S. Okay? So I have a groupoid, I have generators and relations. Okay? So now this is a very easy example, right? I mean, I just took two objects and two morphisms. So this groupoid here is much more complicated. But somehow the idea is the same, so you can think of it in this sense. Okay, now I would like to say what actually are the relations that we have in Birmori. So the relations in Birmori. So I said it's generated by trivial relations and elementary relations. So trivial relations so there are two types of trivial relations. The first type is just between isomorphisms of Mori fiber spaces. So if we have, let's say, alpha 1 up to alpha n. So let me just write identity, but I mean, so whenever I write the composition, it means that like the target matches with the source of the next. So I can compose. And then here identity just means like the source of alpha 1. Okay. So where the alpha I are isomorphisms of Mori fiber spaces. This is one trivial relation. And another one is if we have, so let's say I have alpha 1, chi 1, alpha 2, chi 2 is the identity. Now again, the alpha i's are isomorphisms of Mori fiber spaces. And the chi I are Sarkisov links. Okay. So basically, so relations between automorphisms can be complicated. I don't want to think about it. I call this trivial relations. I'm not saying that these are easy relations or anything. I don't want to care about them. Okay? Because also before I said that in fact in our examples we will send isomorphisms onto 0 always. Okay, so I don't want to care about this. And so the second kind here of the trivial relations. So let me draw a diagram. So if we have, let's say maybe x1 to x1 prime with chi 1. So this just means like we look at diagrams of this form. So isomorphisms here, x2 prime with chi 2. So whenever we have such a diagram, we call this also a trivial relation. So in some sense, this means that we will think of chi 1 and chi 2, they are the same. So we will make an equivalence class. So chi 1 and chi 2, when they satisfy such a diagram, we will call them equivalent. Okay, and the elementary relations. Now, I don't want to be specific at the moment. Let's just say that these are the ones that correspond to a rank 3 vibration. So the relation between Sarkisov links corresponding to a rank 3 vibration. I will later give an example of what this actually means. But the idea is kind of, okay, if we have a Sarkisov links, we have a rank 2 vibration. Okay. Now let's say we blow up 1 point more, maybe such that it's still del pezzo on top. And then this is then a rank 3 vibration. If the top thing is del pezzo, it's a rank 3 vibration. And then it will dominate more rank 2 vibrations. So it will dominate more Sarkisov links, and they will form a relation. So actually, let me draw this picture again in a slightly different way. So let's say we have this relation. Okay, so what this means is that we have. So I draw this again. So with A, B inverse A, B inverse A, B inverse, and in the end we didn't do anything. Okay. Now, so we have now generators, we have relations. Now, how do we construct the quotients? How do we construct these group homomorphisms? So construction of groupoid homomorphism. Okay, so we start with so this is now just like a general overview of how it's done. So let's just say Biomori of X. Okay, so with the Sarkisov program, we know that we have here a description with generators and relations. So let me write in this way. So we have here Sarkisov links and isomorphisms of Mori fiber spaces. And we have relations. So modulo some relations. Okay. Now, the first step is, so what is the goal? The goal is to, in the end, get some quotient that we can understand. Like maybe want to get Z or Z mod 2 or something like this. So like some group that has like a description, let's say. Okay, that's, yeah. And so the first step is that we make this equivalence class that I have mentioned before, so like with these trivial relations. So the first step is we want to get rid of these trivial relations. So we do here, so let's say here, let's say I have here an element I'd have here I have a birational map in Birmori X. I decompose it into Sarkisov links and isomorphisms. Okay. Now I want to send it onto some equivalence classes. So let's say F1 bar, Fn bar. And now this is now, let me write it in. So, okay. This is now, I take now the equivalence classes of Sarkisov links. And I get some induced relations. Okay. So, and now let's say equivalence classes, what I mean here is like that chi prime, or like chi is equivalent to any, so to any alpha chi beta, where alpha beta are isomorphisms. And in this sense also, I send isomorphisms onto the neutral element. Okay, so this is the first step. And now, so okay, just to say like, okay, if we know very precisely, if we know all the Sarkisov links and we know all the relations very well, this means we understand Birmori X very well. But this is not the case. Birmori X is complicated. So we don't understand this object. So we want to, to see what we understand. And so now what we want to do is we want to choose some Sarkisov links that we understand well. Everyone else sent onto 0. So, okay, so just say, okay, so now we go to F on like some equivalence classes of Sarkisov links. And so this is really like a choice, a specific choice. And this choice is different with all the constructions, modulo sum relations. Okay, so here I just mean everyone else is sent onto 0. If they don't, if the Sarkisov links is not among our chosen ones, we send it onto 0. And then maybe later on, maybe we want to neutralize some more elements, or like maybe we want to make weaker equivalence classes. So in the sense that maybe we want to identify more things. So just like that, in the end, we get something that we can understand. Okay. And so this is now a groupoid homomorphism. And then in the end, so okay, so in this way, let's say maybe we go from Birmori X to some groupoid G, fancy G. And then we get, so inside we have Bir X. And then, because this is a groupoid homomorphism, we get a group homomorphism. So this is groupoid homomorphism. Then we get a group homomorphism onto, so G of X, or maybe let's call this phi, maybe G of phi of X. So this is now a group. So now you have this groupoid. And now you look at, so somewhere you have a phi of x. So this is an object. And now, well, the groupoid is connected. And so now you take, you take all the combinations of, so you get a group. So this is then a group homomorphism. And then what remains to do is to study the image of this group homomorphism. Because it's very well possible that here you have something non-trivial, but the restriction is trivial. So yeah. So final step is study the image. Study image of the group homomorphism. Okay, so now let's actually do a construction. So let's look at the following. So let's look at Bertini involutions. And so this construction goes back to Lamy-Zimmermann. And here I want to mention that they did the. So they looked at the proof of the Sarkisov program by Haken and Kernan, which works in higher dimensions. And then they made sure they checked that it works also for surfaces over non-closed fields. Yes? You disagree? This is also true, yes. Yes. Yeah. And then you added the relations in this set. Okay, so let's do the following. Let's take P2. And let's blow up a point of degree 8. So this means that I assume that my field contains a point of degree 8. This is not necessarily the case, but for example, if you take the rational numbers, you do have a point of degree 8. So you blow it up, and now we get a Del Pezzo surface of degree 1. Okay. But now again, so P2 has a pica rank 1. So this Del Pezzo surface has pica rank 2. And so it is a rank 2 vibration. So this gives a Sarkisov link. And in fact, so because, yeah, so this is the, so okay, on Y1 we have there's the Bertini involution. And so it sends this the exceptional curves here onto exceptional curves. And because the pica rank is 2 and the exceptional curves are not fixed, it is sent onto different curves. So here we have, again, we can contract an orbit of -1 curves of size 8 back to P2. And so this is again a Sarkisov link. Okay, so now I would like to construct a group homomorphism with this type of links. So this means I want to send everyone else to 0, but this link I want it to survive. Now, what do I have to check? I need to check trivial relations and elementary relations. So let's first look at elementary relations. So the question is like, does there exist a rank 3 vibration which dominates this link? Okay. So what would you do? You would blow up a point, and you want to check the conditions whether it's a rank 3 vibration. Now, but and so this would be a rank 3 vibration over, so this is over spec K. But now we have Y1 is a Del Pezzo surface of degree 1. So if I blow up a point, well, it's not Del Pezzo anymore. Okay? So this means that there is no rank 3 vibration which dominates this link. It means there is no elementary relation involved. So there is no rank 3 vibration T over spec K dominating this link. So we have no elementary relation. Sorry? So Y1 is a Del Pezzo surface of degree 1. To get a rank 3 vibration which dominates the link would mean that we have here a T on top and a B on the bottom with maps. But now, if you have T over Y1, so one of the conditions, okay, a rank 3 vibration over spec K means it's del Pezzo. But there is no del Pezzo surface dominating Y1. Okay, now what about the trivial relations? So I don't care about automorphisms of P2, okay? I send them onto 0 anyways. But there is another trivial relation, because this is an involution up to pre or post composition with an isomorphism. Okay, but this is for me this is an involution. So this means that well, if this is chi, then chi squared is the identity. Okay, and so what we get is, so we get phi from Biamori of P2 to a free product of Z modulo 2 sets with an indexing set corresponding to these equivalence classes of links. So let me write it as P8, so fancy P8, where I write, so P8 of P2, so this is where fancy PD of X is the points on X of degree D in general position modulo automorphisms, because the base points give the Sarkisov link. Ah, thank you. So general position is over the algebraic closure. So I do base change with the algebraic closure. And so general position means that the blow up is del Pezzo. And I should say that here, let's say here X is del Pezzo. So this is for X del Pezzo. Or actually, if we would have a conic bundle, general position for me would mean that like if you blow up, you get a rank R vibration. So yeah. Okay. Okay, so now this example is kind of cheating, because now I still didn't really tell you what elementary relations are, right? I just told you they don't exist for that dominate here. So. Okay, so let's maybe, so I wanted to give 2 more constructions. So let's see whether my time planning is good or not. So now I want to look at the birational maps between Hirzebruch surfaces. So I take a link as follows. I have a Hirzebruch surface Fn, and I go to some Hirzebruch surface Fm, and I do it in this way. So I blow up a point of degree D, and I contract the strict transform of the fibers through that point. So let me maybe draw. So this is Fn, so this is over P1. So now I blow up So this is a point of degree d. So geometrically, this is the picture. I blow it up. And now I contract the strict transform of the fibers. So let me do more color. Dissonance. So this is the okay, so here I have some surface y. Now, is this a Sarkisov link? So, because now y is not necessarily del pezzo anymore. And in fact, I want that, so let's take such a thing, such that y is not del pezzo. So, for example, we take d to be at least 8. Okay, because if I blow up on Fn degree 8, then it's for sure it's not del pezzo. Okay, but this is now still a Sarkisov link over P1, because what we do here, so everything here is over the base. And so this here is still relatively ample over P1. Because, yeah. So here it's still relatively ample because, so for example, there's no like -2 curves that are contracted over here. So it's really a conic one. Okay, and so here we have. Okay, so now what I want to do now is I want to let these people here survive, and everyone else I send them onto 0. Okay, so these are not, so this is a Sarkisov link. So maybe just to say, like, if I would blow up a point such that, so let's say we have a fiber defined over the field, and I take a point of degree 2 on which sits on a fiber, then if I blow it up, it will not be a rank 2 vibration. It will not be relatively ample over the base because we have a -2 curve. Because the fiber here has self-intersection 0. If I blow up 2 points on it, it becomes -2. So this would not be a rank 2 vibration. But here it's all good. Okay, so this means now we have to look at the elementary relations. Okay, so I don't want to worry about many things, so let's do the following. So here for this case, let's make the following equivalence relation. So I say that a link chi I, which goes from some f ni to some f mi, blowing up point of degree di. Okay, so I take 2 such links, and now I say that chi1 is equivalent to chi2 if d1 is equal to d2. Okay, so I just want to look at the degree of the points that we blow up. I don't want to, yeah, so also like if I go between different Hirzebruch surfaces, I don't care, I just care about the degree of the point that I blow up. Just to have an easy life. Okay, so now let's look at the elementary relations, because now with this definition, I don't have to care about the trivial relations much. Are they still here? No. No. Ah, yeah, they are. Yeah, right, because now, okay, anyways, automorphisms are sent onto 0, but now yeah, so if chi1, chi2 is the identity, then they will have the same number of points blown up. Okay, so what kind of elementary relation has such links involved? So what we do is the following. So I take one, so let's say fn1 to fm1, or maybe I just say n to m. I have a link chi1. Okay, and so I have p. So this is over p1. Okay. Now, first of all, an elementary relation over spec k does not exist because of my assumption that I take d of large degree. Right? I wanted it in such a way that the surface here is not del Pezzo anymore. So in particular, there is no rank 3 vibration over spec k that involves this link. And this is why I chose d large, because I want to have only a few relations. Okay. So now how do we get the rank 3 vibration over P1? What we have to do is we need to blow up a point. And so we obtain T. So now T over P1 is a rank 3 vibration. Now this also means that we blow up a point on different fibers than the point D. So in the first link, let's say we blow up 2 points, and now on the blow up, can I do it? Okay, and now I blow up points on a different fiber, okay, so that I get a rank 3 vibration. And any rank 3 vibration that involves this link is of this shape. Okay? So now I have like this. Okay, so this is my T. So here I have T. I didn't give a name, but this is Y. Very beautiful. T, Y, F, N. Okay. So now, okay, good. So now let's look at this. So we have here T, we contract red, and then we contract yellow. Instead, I can first contract yellow and then contract red. Oof, okay. Okay. So, what do we have? So now I have in Fm, and I blow up the red point. Okay. So I blow up the red point. So let me draw this fiber here green. Oh, I hope no one is colorblind. So this is green. So I can, if I blow up red, I can contract green. Okay. And I go to some Hirzebruch surface FR. But now, the surface that we get here, this is a rank 2 vibration, right? This is exactly a Sarkisov link that I described before. This is a Sarkisov link chi2. Okay, good. So let's look again at T. So we first contracted yellow and then green. But now we can first contract green and then yellow. So let's do this. So green and then yellow. Oopsala. Okay. But now we can do the same thing again, right? So we are on FR. We blow up the yellow point. So we can contract the strict transform of the fiber through the point. So I need one more color. So we blow up yellow. So this is lila. Okay, so I blow up yellow, I contract purple, and I go to some Fs. And again, this is a Sarkisov link. Okay, and so now what do I do here? Now I can, so I do first green and then purple, so I change the order. I do first purple, oopsala, and then green. Okay. And so now let's look, so what happens? So now I have Fs, I blow up green. So what happens? I blow up green, this means I will contract red. Okay. And so this means also that here we finish the diagram. And this is also a Sarkisov link. Oh. So here, so actually now now I see that I used here twice yellow, right? So this was in fact not yellow. But it was. So okay. I did a huge, okay. So, okay, I didn't, so what I want is that this here is purple. So now just repeat everything that I said. But when I said yellow, I meant, well, okay, is it okay? So, okay, so let's do it again. So now I don't start with this picture, unfortunately. Okay. So, okay, let's do it in this way. So what I said is I blow up yellow. So now let's do it here. So now I can contract purple, and I go to this. Okay. So this is Fm, and this here is Fn. Okay. So what I do is the link. So okay, what I do is I start in Fn, I blow up purple, I obtain this here, and I contract to yellow. Okay. And then I blow up yellow, and then red. So now it's good. Yes? Okay, so I can. So I blow up purple, contract yellow. Okay, this is one link. Now on Y, I look for an elementary relation. So I look for a rank 3 vibration. I blow up a red point. Now instead of green yellow, I can do yellow red, and so on. Okay, so we have found this elementary relation, and they are all of this shape. Okay. But now we see that. So yes, so if I write here the degrees of the points, so this is all D. This is all D. Then here, the red is E. But then this also means, because here red is E, this means that also green is E. So now when we look at this, let me make this a bit more abstract. This is just a square. So this is one link, chi1. This is a link, chi2. This is a link, chi3. And this is a link, chi4. Now, what are the equivalence classes of these links? So chi1, so right, this was a DD link, so DD, but also chi3 is a DD link, chi2 is an EE link, and chi4 is also an EE link. Okay? So this means that this and this, they are in the same equivalence class. Okay? And so this means now the group homomorphism that we get. And so to get rid of this, because right now this means that the relation that I have to look at is chi1, chi2, chi1, chi2. Okay. So maybe I can write in this way. So chi1, chi2, chi3, chi4, right? So this is what I have a priori. Now this is then mapped onto chi1 bar, chi2 bar, chi1 bar, chi2 bar with this relation. And now what I do is I just do everything modulo 2. So I will go from Birmori. I will go to direct sum Z modulo 2 with so now I can do it with B at least 8. Okay, because then this is just, so I make it abelian. So yeah, modulo 2, so this is just, 0. Yes? So here, yes, but also just because if chi1 is a DD link, then also chi inverse is a DD link. So they are, okay, and now, so this is now on the level of Birmori. So now you have to look at it on Bir. And what you can do is, okay, so if you start in P2, you blow up a point, you're in F1. Okay, now you do a DD link. You go to some, I don't know, FM. Okay, and now I can do like, with small steps, I can go to Fm minus 1, so I blow up one point and I contract the point. Tick, 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 so I do small steps up, back in F1, and then I go back to P2. So what I want to say with this is, okay, so let's look at the Sarkisov links. This is mapped onto 0. Everyone here is mapped onto 0, but this guy survives. Just to say that this restricts to, so on, okay. So we get from P2, we get really a surjective map onto. Oh, I'm so sorry. I'm so sorry. Yes, it's sorry, I didn't realize. Sorry. Yes, I would, yeah. So this would be relations of rank 1, rank 2, and rank 3, yes. Yes. So I think it's a very good way to see it conceptually. Yes, I absolutely agree.